Assalamualaikum and a very good day to the respective panels and guests. My name is Faisal. I am from University Naga National. For today, I will be presenting our work, which is improving event classification using Hamilton filter for distributed acoustic sensing. As a sensor, the faisal TDR is an effective system to detect vibrations and acoustic waves with high sensitivity. By integrating coherent relic backscattering light in sensing optical fiber cables, making an effective tool to be used for distributed acoustic sensing applications. Among its strengths include long sensing range, high environmental vibration sensitivity, and great anti-electromagnetic interference. However, the phase of TDR is limited to only collecting environmental vibrations without providing more useful information. Shown is the phase of TDR setup that was used in the lab. As a primary light source, a distributed feedback laser containing of an ultra-narrow line wave is emitted as light. The light is modulated by the AOM to produce pulses and is amplified by the EDFA. It is then split into a 91:1 ratio, and two mechanical PZTs were vibrated at different frequencies to simulate events. The Rayleigh backscattered light is amplified by a second EDFA, and it is then acquired and displayed by a digital oscilloscope. Recently, there were works that propose methods to obtain more valuable information from the phase of TDR system. Among them was in 2013, where Wu et al. Proposed a multi-wavelet decomposition technique to separate temporal signals into different scales containing unique components. By merging only specific components, intrusion signals can be obtained without the presence of external interferences. From their work, 89.19% accuracy were achieved. In 2017, F. et al. Implemented the male frequency structure coefficient. The MFCC is a typical signal processing method which approximates the human's auditory system to extract relevant information from the phase of TDR data. 98.02% accuracy was achieved. In 2020, Shi et al. Proposed a small-scale convolutional neural network (CNN) model. The CNL model was used to extract features from the temporal spatial domain and was successful with an accuracy result of 91.77%. In this work, we propose the Hamilton filter as the feature extraction technique. The Hamilton filter is a type of human auditory filter for approximating sound signals being synthesized by the human auditory system. Much like a bandpass filter, it consists of a bandwidth that filters out signals with frequencies outside of the bandwidth range, resulting in only targeted frequencies to pass through the bandwidth. The output of Hamilton filter is Hamilton frequency structure coefficient, also known as the FCC. The time response of the FCC is described by question 1. Among its advantages include it is operable in time and frequency domain and have good performance in processing data containing noise. It has been applied in various fields of applications, which include automatic speaker recognition, robust speech recognition, and underwater target feature extraction. To implement the Hamilton filter, 3 phases will be carried out in succession, which are data organization phase, followed by feature extraction phase, and lastly by feature classification phase. In data organization, the first step is to arrange and manage time domain data, which are PCT pulse waves of 300 Hz, 700 Hz, and 900 Hz using MATLAB. Second is to extract each arranged data in step 1 using the simple differential and normalized differential method. And lastly, create 2 new sets of data sets produced in step 2 and label them as extracted simple differential and extracted normalized differential. In feature extraction phase, the first step is to wrap each extracted datasets into time frequency domains using the Hamilton filter, also known as gamettogram. Second is summing up each row of gamettogram to produce the GFCC. Third step is to truncate GFCC data by selecting the peak range of interest to avoid high dimensionality problems. Fourth step is to repeat steps 1 to 3 for all other 230 samples of data. Lastly, group resulting data into a 60:40 ratio for training and testing purposes for machine learning. For classification phase, support vector machine is used as the primary machine learning model. For step 1, k-fold cross-validation is used to fine-tune and test yield. For step 2, SVM is used to train the reference and trial dataset. And lastly, step 3, detection results from the simple differential and normalized differential were evaluated using cross-correlation method. To evaluate the performance of the classification result, the first step is to train a 4 nearest neighbor method using the built-in fit, seek, and end function in MATLAB. Lastly, is to obtain the coefficient matrix result by correlating the results between the 4 nearest neighbor method and to predict the response classifier using the built-in confusion map in MATLAB. As for the results, 5 types of results is presented, which is written by each phase. The event detection results are obtained in data organization phase, where 2 different event detection methods were used to detect positive events. Figure 2a represents the result of implementing the simple differential method, while figure 2b represents the result of implementing the normalized differential method. Based on figure 2b, the normalized differential method produces an overall higher amplitude reading of the detected event present between 4,750 and 4,900 sample points. This is due to the method of the normalized differential that enhances the amount of noise equalization within and along the fiber, enabling for better detection of events. For the result of feature extraction, figure 3a shows the GFCC data that has been successfully obtained for implementing the Gamerton filter, while figure 3b shows the GFCC data that has been truncated to avoid high dimensionality problems. For the result of feature classification phase, figure 4 shows the classification result implemented by using support vector machine. Based on figure 4, the classification performance by the simple differential method surpasses the normalized differential method. This is because the handcrafted point scatter for simple differential maintains their distance from the hyperplane as compared to normalized differential, which is less consistent. Another point is that feature separation of the simple differential from the hyperplane has relatively larger margin compared to normalized differential method. For cross-correlation result, table 1 revealed that each dataset is susceptible with positive correlation. It can be expected that the cluster between pulse signals can be achieved and a slight decrease in classification performance between the outputs might be expected. For the classification performance evaluation result, table 2, 3, 4, and 5 show the confusion matrix score that represent the accuracy of the classification performance. From the results, it is observed that the first 2 diagonals show the correct classification by SVM, with all 10 feature points successfully being classified according to its class and none being wrongly classified. This is true since figure 4 shows that every feature point lies within their respective regions. To conclude, this work has proposed a processing system to distinguish between different events happening within the sensing regions of the phase of the system. A comparison work between simple differential and normalized differential have shown that the normalized differential proved to be a better event detection method, as it produces a higher amplitude value reading. However, the classification result from the simple differential Gamerton filter combination have proved to be better than the normalized differential Gamerton filter, achieving a confusion matrix score of 100% for classification performance. As acknowledgement, we would like to thank United R&D as MVD for the generous support in supporting this research. Thank you very much.